Okay, guys, we're gonna start. We're out of time. The next chapter, guys. This chapter deals solely with looking at relationships with lines, and when lines either intersect or don't intersect with other lines, and we can have 2 or 3 or 4 or 5 of these things. What relationships then exist? What happens with those type of things? And then we start talking about. Okay, well, what if some of those lines, what if we place a condition on some of those lines, like maybe make 2 or 3 of them parallel, or make 2 of them perpendicular, and then what does that relate to then, or create for angles, and how does that create relationships with the other lines that are present? Okay, so that's what this chapter is all about. So in order to kind of start talking about these core concepts, we need vocabulary. We need to make sure that we're all on the same page with vocabulary. Some of this vocabulary stuff that you've learned since like the 3rd grade. But in the 3rd grade, they were poorly written vocabulary words. Okay? Because at that age, we can understand what it means to be parallel, but maybe at that age, our minds, just because of biology, are not developed to understand complex things like planes and 3-dimensional space and that kind of stuff. So they took your vocabulary words at that level and they made them a little bit easier to understand. Okay? Well, at this level, we have to put those words back in that they took out. Okay? So the first one that we're going to talk about is parallel lines. Okay? Parallel lines. The word that they took out when you were in the 3rd grade, they started talking about things that are parallel, is the word coplanar. Okay? Because at that age, the argument is that we're not developed to determine and understand what it means to have a plane, and then what it means to have 2 lines that are in the same plane, like coplanar means. So they took that out. If I take that out and I read this parallel lines are lines that do not intersect, you would probably agree that that's the way you've learned what parallel lines are, right? Okay? Not a new definition, but we're going to add in that phrase or that term that they have to be coplanar. Okay? They have to be coplanar. And that means if our whiteboard is a plane, okay, if I want lines to be parallel, they both need to be in that whiteboard. Okay? And I'll show you kind of the difference here in a moment. But in talking about parallel lines, there's a lot of different maybe definitions or alternative definitions that you've maybe talked about in the past. And these are things that I will use as well. Okay? Parallel lines. Okay? Characteristic of them. Or maybe you said last year that there are 2 lines that have the same slope, right? Okay? That's a characteristic of parallel lines. Even though, guys, when we're not maybe working inside the coordinate plane, every problem that we do, guys, the coordinate plane is just a way for us to find positions of things. So if our problem doesn't have a coordinate plane, we can always lay a transparency over the top of what we're working on and put it in the coordinate plane. Does that make sense? Okay, so the idea, I guess what I'm trying to get to here, is that if I start off with something that looks like this, maybe our problem is starting off with that, just a blank screen, right? Okay? But we can take and lay on top of it our axes. And now, when I lay my axes on top of that, now I can start talking about maybe certain positions. Does that make sense? Okay? So it's always there. The coordinate plane is always there in everything that we do. Okay? But whether we highlight it in an effort to use it is a different question. Okay? So that's something to think about as we're doing this. So my argument is, even though we're in a different subject here, we're talking about geometry, and last year we did slopes, you're always in the coordinate plane. Well, every line I give you, whether it's in the coordinate plane or not, the coordinate plane can be added to where you can determine what the slope is of that line. Okay? So parallel lines, where lines have the same slope. Another way that you might have determined what parallel meant was that there are 2 lines in which the distance between them was constant. The word constant means never changes, right? Okay? So two lines in which the distance between them never changes. Okay? Got a bullet there that says if you think about like a railroad, think about the rungs on a ladder. Okay? Think about the grid on the drop ceiling above us. Okay? The distance between maybe those north and south lines or the east and west lines of that grid on top of or on the ceiling, the distance between them is the same, so that when we go to Lowe's and we buy a 2x4 panel to fit inside that grid, any 2x4 panel is going to fit. Does that make sense? And that's the need for understanding what parallel is in regards to the distance between the two lines is a constant. What we talk about then is, I'm going to put this up in front of us, and over here, so I've got these two lines. Okay, we got those two lines that just kind of highlighted, went bold there. You see algebraically on the left-hand side, they both have a slope of 0.47, right? Okay, so 0.47 is their slope. Okay, now we see that they're parallel, so they have the same slope. This here is the distance between them. Okay, well, what are we recognizing as I slide that distance through? What are we recognizing? That 3.2 stays the same. Okay, if this was like a railroad, and the way I've set this up, I actually have to do it this way. Okay, so let's say I had those two lines. Now as I move, it's messing the line up too. It's not doing what I want it to do. I want this line to not be parallel, and then you would see that distance is going to change, right? At 2.89 right now would change as I move it through. And the idea of a railroad is the axle base, the wheel base of my train is never going to change, right? So if the rails were to converge, okay, my train is going to either bind up or it's going to fall off the track, right? Okay, so there's a lot of, in order to keep us safe and to keep transportation and freight and all that kind of stuff moving, engineers need to understand the idea of parallel. Okay? And in this case, the idea that the distance between the two rails has to be the same. Okay? All right, why do we talk about coplanar? Okay, why does that have to be part of our definition? There are going to be things that we deal with. If I just say there are two lines that intersect, or that do not intersect, and that's my justification for what parallel means, that incorporates some things that don't have all the same relationships that are existing maybe in this situation right here. Okay? And what I mean by that is if I were to look at these two lines, okay? Now I'm in three-dimensional space here, okay? And if I start to rotate this, you can kind of see how those lines, maybe one of them's coming like right at you right now, right? That A to B is coming right at you, C to D is going left to right. Okay, or if I want to do this, the CD is coming at me, and the other one's going left to right. But those two lines, would you agree they never intersect? Okay, but now the argument is, well, what if I were to find the distance between those two things? The argument that we make in regards to the distance there, whatever that is, so that's saying it's 4.46. But now as I move these, okay, how do I judge how to keep that distance the same? Does that make sense, everybody? Okay. So that's a problem. Does anybody know what these two lines would be called to one another? Let's see here. Let's see if I can do this. B is at G equals the X of B, comma, the Y of B, comma, the Z of B, but minus 1. All right. you guys agree that this plane right there contains that line AB, or that segment AB? Does that make sense? Okay. This line here intersects that plane. So DC, that intersects that plane one time. Okay. When this happens, those two lines are non-coplanar, right? We refer to those as being skew. S-K-E-W. Okay. Now here's the idea. Here's maybe somewhere that you've seen this before. Okay. If I'm going to barbecue, I'm going to chop up some meat, I'm going to chop up some vegetables, and I'm going to go to my grill. And before I put them on my grill, I'm going to put those vegetables and meat on a skewer, right? And the idea is the plane represents that meat or that vegetable or whatever, and this line here is skewing, or is the skewer that would go through those. Does that make sense, everybody? Okay. In the past, when I didn't have GeoGebra, this is the picture that I would give. Okay, that's the idea. That would be the skewer, and you got your plane here. That is the meat that you're cooking. So you guys have seen that word skew before, okay, or derivatives of that word skew in real life. And to us, what it means mathematically is that they are two lines that are non-coplanar and never intersect. Okay. When we take a test or a quiz, I'm going to ask these, so these two vocabulary words will be back to back. Okay. There will also then be a question that says true or false, parallel lines are lines that do not intersect. Okay. Or I might ask the phrase, all lines that do not intersect are called parallel. And my hopes are you to answer that false, because some lines that do not intersect are called skew, right? If I rephrase it, said, all coplanar lines that never intersect are parallel. And I ask you to say true or false. There you would say true, right? Okay. So it's very important that we understand the difference here. Coplanar, parallel. Non-coplanar that never intersect, we call them skew. Okay. A common picture that they give you to determine whether things are parallel or skew is that they'll give you one of these rectangular prisms, and they'll say, focus on maybe that line right there. Maybe that's a bad choice in color. We'll ask us to focus on that line. I don't know if that's any better. And they'll say, if you're focusing on that line, which segments or which other lines would be parallel to it? Okay? And now the question is, would we agree that that line right there is parallel? They're both in that yellow plane on top, right? So they're coplanar. They're not intersecting. Those would be parallel. Okay? Now the next question would be, are these two? Okay, so get rid of that one. So now, are those two parallel? And the argument would be yes, they're in that face of that prism that is closest to us, right? They're in that plane. Okay, and there's one more up there that is parallel. Okay, and that one more might make more sense to be able to view it in something like this. So let me give me a quick minute. Put a polygon in here. That is not what I wanted. Makes no sense. There we go. All right, so if I look at this prism, okay, and I start talking about segments that are parallel to maybe, let's use this segment right here. Okay, that segment, that blue segment, I asked you which ones are parallel. My argument would be that one there would be parallel, right? You agree that they're both in kind of that plane right there, right? Okay. This one here. Need that to go away. There we go. When I working in this 3D, because I've got other programs that have to be open, especially the recording, things will be slow. It just eats up a lot of RAM on my computer. So just bear with me. Would you agree that that blue line right there and this one back here are parallel? Okay. There's one more, and it's going to be this one right here. Okay. It's going to be that blue one, GF. Now, the reason that one, and people say, well, that's not in the same plane as A to D. So people argue that those two blue segments are not in the same plane. However, if I look at that idea right there, is that one plane right there? Okay? Are they both in that plane? And that's the issue with some of the pictures and some of the renderings that they give you in your homework questions, or even on the end of course exam. Just because what they draw there doesn't show that plane that's going through the interior of that prism, doesn't mean it's not there. Does that make sense? Okay. Our postulate to say any three non-collinear points, there's exactly one plane that encapsulates them or contains them, cannot be, can't throw that to the side and say it doesn't work in this situation. Okay. Even though it's not drawn there, we need to know that plane is still able to be drawn. Does that make sense? Okay, so that's what we're talking about there with those lines that are parallel. Then they ask you to do the same thing with skew. Okay, so then skew would be, as long as I choose two lines that do not intersect and are then in different planes, so we'll just do one of these. Would you agree that that one there and maybe that line right there would be skew? Does that make sense? I think it's hard to see sometimes in two-dimensional renderings of three-dimensional shapes how things are skew and how things are parallel. I think it's a great tool for us to be able to analyze things and look at something like this, because then it makes it allow us to, kind of like we had it in our hands. Okay. Parallel planes. Planes can be parallel. Planes don't have to intersect all the time. Okay. If they do intersect, they form a line. Okay. But if they do not intersect, okay, then they're called parallel planes. Like the ceiling and the floor, they do not intersect. Okay. Be like the wall to your left and the wall to your right. They do not intersect. They're parallel planes. Okay. One thing that we got to pay attention to and be cautious of, again, it goes back to how we render our pictures. If we are talking about like segments, for instance, these two segments right there, they don't intersect, right? Okay, but will they eventually intersect if we extend them like lines are supposed to be extended? And that's what we have to be able to justify. Those segments would not be parallel, because when we extend the lines that they actually come from, create that line there, and then that line there, they are eventually going to intersect. Does that make sense? Okay. The only time that those two lines would be parallel would be if, or these segments would be parallel, would be if maybe we did something, let's see here, like that, where now, when I make this line and that line, they do not ever, as far as they extend, will never intersect. Does that make sense? So segments in rays can be parallel. Segments in rays can be parallel. We just have to justify that, to make that argument, is actually look at the lines that those things come from and then see if those lines are parallel. Planes are the same way. Okay? If, for instance, let's say we've got a weird, maybe three-dimensional shape here where I don't know if I'll be able to, I should be able to do this. Okay, so if I look at that plane right there, that orange one, make it yellow, easier to talk about, see. That yellow plane, okay, and let's say that yellow plane, okay, do they touch? Are they intersecting at all? No, okay. But if I take the plane that this one extends as, okay, and then take the plane that this yellow one extends to be, do those planes intersect? Does that make sense to everybody? Okay, so we would not be able to say that those yellow planes are parallel, okay, because the full plane is actually, you know, whatever color that thing is and whatever color that thing is, it'd be those planes, okay? So we just have to remind ourselves of that as we're kind of analyzing whether things are parallel or not. Okay? I'm not going to skip through these questions because I think the discussion we just had would allow us to answer those pretty easily. Okay? This next part, guys, is going to be something that we will talk about for the rest of the year. It is a very key point to allowing us to prove a lot of relationships that exist beyond this. Okay? You guys remember last year working with sine, cosine, and tangent, and like you worked with if we were like measuring the height of the monuments out there or the statues out there in the courtyard, we could take the shadow of the statue, we could take our shadow, we could take our height, and we could use those in a proportion with sine, cosine, tangent to come up with the height of the statue. You guys remember doing that stuff? You didn't do that? Okay. If you did do that, the reason you're able to do that is through the use of alternate interior and alternate exterior angles, which is through the use of understanding this image right here and transversals. Okay, so we'll do that again this year. Okay, but it's not until chapter 7 that we can do that. Okay, we got to learn this, some stuff about ratios, and then we'll be able to merge those together to learn a new concept. Okay, to do some measurements. But I just want to try to give you an idea of how important this is. This stuff is going to be used over and over and over again to come up with new ideas. But a transversal is a line that intersects two or more coplanar lines at distinct or different points. Okay? Transversal is just a line that intersects two other lines. Okay? But all these things need to be coplanar. Okay? So what that does for us is it will continually give us every single time, it will give us an image kind of like this. Okay? Or it'll give us an image. Let me get a new one here. It will always give us something like that where we have these two lines being intersected. Okay, so the red lines, we don't have a word or a name for those red lines, but that black line is called the transversal. Okay, notice that black line crosses over two lines at distinct points or different points. We want that image to show up. We want this picture. Okay? Now it might be like this. You know, it might be where the transversal is more kind of vertical like that, okay, where these two lines are maybe more like that, okay, or so that looks like they're almost kind of parallel, but they don't have to be. Okay, so we're looking at this image. Does that make sense, everybody? Okay, so this black one is always the transversal. Now, the idea is that we want this to happen, and they use some key terminology here, is that they have to happen at distinct points. Okay, we are looking for this black line to intersect the red ones at G and H. Would you guys agree that G and H are different ordered pairs? Okay, down here, G and H are different ordered pairs. What happens if G and H become the same point is the idea that we don't have now a total of 3 lines. Does that make sense? And when we do that, when G and H are the same point, this image that we're interested in kind of dissolves. Okay? And the relationships that exist inside this image and all the images like that are kind of consistent. But yet they are different than the relationships that exist here. Does that make sense? Here we've got kind of vertical angles. Here we've got more stuff. We've got a lot more other relationships that are useful and important to us here. So we're looking for a transversal to be something that intersects 2 lines at distinct points. The key phrase there, distinct points, forces L and M to be different lines instead of the same line. Okay? When you have this, you have the distance, or I guess the space between L and M. The space between L and M, we call that the interior. Okay? So you got regions in between your 2 lines, call that the interior. The regions outside your 2 lines, we call the exterior. Does that make sense? The interior and exterior, those are locations based on the 2 lines that are being intersected. Okay? Now, we also have positions based off of the transversal. Okay? Every time you do this, you're going to get 8 angles. Okay? Angle 1, 2, 8, and 7 are in the exterior in regards to our 2 lines, right? They're in the blue exterior region. Okay? 3, 4, 5, and 6 are on the interior of those 2 lines. Okay? If I ever say, hey, identify your exterior angles, or identify your interior angles, that's what we'd be looking for. Okay? And they'd be groupings of 4 angles each. But we want to maybe narrow that down and be able to talk about maybe just 2 sets of angles. Okay? So the next thing we do is we start talking about these 4 angles. And they are on the same side of the transversal. Okay? So if I look at the same side angles, there's 4 of them. 2, 3, 6, and 7 are on the same side of the transversal. 1, 4, 5, and 8 are on the same side of the transversal. Okay? We call those same side angles. Now, if I look at 3 and 6, use those 2 adjectives that we just talked about, interior, exterior, or same side, and talk about how you would call 3 and 6. How would you identify those? Where are they in regards to the transversal? Are they on the same side or are they on a different side? Same side. Where are they based on lines L and M? Are they in the interior or exterior? Interior. So 3 and 6 should be called same side interior angles. Does that make sense? Okay. Because of their positioning in regards to L and M, and then their positioning towards T, the transversal. 2 and 7, okay? Now, you won't hear this word very often because they're not useful angles in anything that we do beyond this, but 2 and 7 are same side, what? Same side exterior, okay? We like to eventually kind of make comparisons with that angle there and that angle there eventually. Okay? They are on different sides, right? Okay, you jump from one side to the other side. What's a word that allows you to go kind of back and forth? I go back and forth between 2 things. It starts with an A. You guys know what AC and DC are in regards to circuits, electricity? DC stands for direct current. AC stands for, anybody know? It goes back and forth, turns on and off. Alternate current. You guys know that? Okay. So the word I'm looking for here, going back and forth, is alternate. Okay? Would you agree that 3 and 5 are on alternate sides of the transversal? Okay? So what we would call 3 and 5 is alternate interior. Okay? 4 and 6 are also a pair of alternate interior. Okay? What do you think you would call 2 and 8? Alternate exterior. Good. Okay? So I've got some definitions here to classify those things. Alternate interior. Okay? By definition, they are non-adjacent interior angles that lie on opposite sides of the transversal. So we'll be looking at the blue angles 3 and 5, and the red angles 4 and 6. Okay? The key thing here is that they got to be non-adjacent. We don't want to talk about angles 4 and 3 as a group. We already know stuff about 4 and 3 as a group, don't we? 4 and 3 are a linear pair, right? So that's a relationship that we can use that is true here, but it's not nothing new to us. So we don't want to talk about 4 and 3. We don't want to talk about 5 and 6. Okay? We want to talk about 4 compared to 6 and 3 compared to 5. Those are alternate interior angles. Okay? If you take the word interior out and replace it with exterior, you get this definition. Okay, and I know we got about 4 minutes here, guys, and I got to get through these for you so you can be successful in your homework. So I apologize if you don't get this all written down right now, but I'll give you some time to write it down tomorrow. But alternate exterior angles. Okay, same exact phrasing, non-adjacent. Now instead of interior angles, it says exterior angles that lie on opposite sides of the transversal. So 1 and 7 and 2 and 8. Okay? Now the purpose of us doing this, the purpose of us being able to identify these angles is eventually we're gonna force a condition on line L and M. We're going to force line L and M eventually to be parallel. And then when they're parallel, something really neat happens with angle 1 and 7, something neat happens with 2 and 8, something neat happens with 3 and 5 and 4 and 6. Okay? These angles are same side interior, so 3 and 6 are same side interior, and 4 and 5 are same side interior. Okay? They're just interior angles that are on the same side of the transversal. Okay, and again, I apologize for going a little bit quick with this, but I want to get to corresponding as well. Corresponding, if we think about what the word corresponding means, this is a terrible definition. This contradicts everything I've told you about definition. Corresponding angles are on the same side of the transversal T and in corresponding position. Well, I just used the word corresponding inside of that definition, right? So I don't know what corresponding means. I really don't know what this definition means. Corresponding means matches somehow. Okay, mathematically we usually say matches position. Okay. But if I think about like soccer practice and football practice and maybe tennis practice, do they all correspond and schedule-wise? Are they all at the same time on the schedule? Does that kind of make sense? They're all after school, okay? If I ask you whose room or what room in this building corresponds to this room but on the first floor, you would say what? The office. Mr. Jesco's room or office is right below us, okay? If I said whose room corresponds to Mrs. Fleming's on the first floor, you'd say, oh, Oliver's is Mrs. Hughes. Fleming's would be McCoy's. Okay? So you see that idea of first floor, second floor, it corresponds to position based on their floor. Okay? So if this is my first floor here, if line L is my first floor and M is my second floor, okay, or vice versa, how you want to look at it, would you guys agree that 2 and 6 are kind of corresponding spots? If I took line L and landed it on line M, do you see how 2 and 6 would overlap? 3 and 7 would overlap. 1 and 5, and 4 and 8. Okay? So those are corresponding angles. And again, eventually, when we force a condition on lines L and M to be parallel, it will be something very useful about angle 2 compared to angle 6 in their measurements. Okay? There is an assignment, 3.1, mostly just kind of giving you a picture and say, okay, identify these angles. What kind of angles are they? Based off our vocabulary, give us some pictures and ask you, are these lines parallel? Are they skew? That kind of thing. Should not be extremely difficult. Tomorrow, we'll force those lines to be parallel and see what relationships then exist when the lines are indeed parallel. Okay?